In one of the grandest equations of the cosmos, the largest number represents a gap in our understanding. For more than 2 decades, scientists have called this gap dark energy, an explanation for why the universe's expansion is speeding up. It's a concept that works mathematically, yet remains purely hypothetical. To this day, no one has ever detected it. But what if the answer isn't an energy at all? What if it's hidden within the very fabric of spacetime itself? The accelerated expansion of the universe was confirmed in the late 1990s through observations of distant type Ia supernova. These measurements didn't align with existing models, which predicted a universe that was either slowing down or static. To reconcile the observations with theory, cosmologists introduced a new component into the equation: dark energy, a mysterious force with a repulsive gravitational effect, pushing the universe apart at an ever-increasing rate. But dark energy has always been more of a mathematical adjustment than a discovery. We have no idea what causes this phenomenon, which is thought to make up roughly 68% of the universe. The standard model of cosmology, known as the Lambda-CDM model, is built on this assumption. This model aligns incredibly well with countless observations, from the cosmic microwave background radiation to the distribution of galaxy clusters. Yet at its core lies the lambda constant, dark energy, a placeholder for something we still don't understand. But what if this fundamental assumption is flawed? What if, instead of adding a new, unknown form of energy to the universe, we need to rethink the geometry that underpins our equations? A new study, published in the Journal of Cosmology and Astroparticle Physics, asked this very question. An international research team from the Centrum for Advanced Technology, Microgravity, and the Transylvania University of Brasov proposes a radical alternative. The team modified the geometry underlying Einstein's equations, using an extended mathematical framework called Finsler geometry. Standard relativity treats spacetime as uniform and consistent in every direction. Finsler geometry, however, relaxes that assumption. In this framework, spacetime can have subtle dependencies on direction or motion. You can think of it like a fabric whose weave isn't the same in every direction. On small scales, this difference is imperceptible. But over cosmic distances, these tiny variations can accumulate and produce significant results. The research team applied this new geometry to the famous Friedmann equations, which describe the expansion of the universe. The result was striking. The equations naturally produced an accelerated expansion, even in a vacuum, a universe with no matter or energy in it. In other words, there was no need for a dark energy term to drive the acceleration. Acceleration emerged as an inherent property of spacetime geometry itself. This finding doesn't overturn modern cosmology overnight, but it suggests that the cosmic acceleration we attribute to a mysterious force might actually be a reflection of how spacetime behaves on the largest scales. This idea is part of a broader shift in theoretical physics, where scientists are looking for solutions not by postulating invisible substances, but by examining the structure of spacetime itself. One of the most elegant aspects of this model is that it doesn't contradict existing observations. At lower energy levels and smaller scales, it remains consistent with the predictions of standard cosmology. It doesn't invalidate the observations that built the Lambda-CDM model. It simply reinterprets their underlying cause. According to this approach, dark energy isn't a new thing that was added to the universe. Instead, by removing a fundamental assumption, the geometry itself is allowed to drive the acceleration. If this holds true, dark energy may not exist as a separate physical entity at all. It might simply be a parameter pointing to a deeper, more complex structure of spacetime. This isn't just a minor tweak to the equations. It's a fundamentally different way of viewing the universe. It challenges the assumption that an unknown energy is pushing the cosmos apart, suggesting instead that the expansion is woven into the very fabric of reality. But an elegant theory is not enough. It must be tested against observation. The Lambda-CDM model remains dominant in cosmology, because it fits the data gathered by telescopes for decades with remarkable precision. For the Finsler-Friedmann model to be taken seriously, it must pass this rigorous test. Researchers will now confront this model with key cosmological probes. First, supernovae. As the original evidence for cosmic acceleration, these stellar explosions remain a benchmark for testing the history of cosmic expansion. Second, the cosmic microwave background, CMB. The tiny temperature fluctuations in this ancient light encode the geometry of the early universe with extraordinary precision. Third, baryon acoustic oscillations, BAO. These cosmic rulers are sensitive to the expansion rate at different cosmic epochs, providing a way to check how accurately the model maps the universe's past. And finally, gravitational lensing and structure formation. The way matter clumps together across the cosmos offers another powerful method for probing the underlying dynamics. If this new geometry can match or even improve upon the predictive power of the Lambda-CDM model, it would represent a major paradigm shift. Not the discovery of a new thing, but a reframing of the laws that govern the cosmos. This is still early work. Dark energy remains the standard explanation because it provides the best fit for what we currently see. Whether geometry can fully replace it is a question that only data can answer. But a new possibility has been opened. The question of what is pushing the universe apart may have been the wrong one all along. Perhaps the real question is, isn't the universe simply built to expand? The answer lies in the observations yet to come.